Here's your integrated 3 lecture for 10.3.3, what is E? So in this one, if we would have been in our class together, we would have gone through and kind of discovered the constant E. But I'm asking you to watch a number files YouTube video. So that I think I assigned that for you guys to watch, and they go ahead and take you through what E is and how it was discovered. But if we would have done this in class, you guys would have done that yourselves by doing this problem. But since we're not in class, we're gonna kind of just let you watch the number files video. I do want to point out that as you were doing your calculations, you would have kept plugging in numbers, and you would have gotten numbers that are very, very close to 2.718280, and that is what the value for E is, or it's very close to the value for E on your calculator. Let me get my calculator. So if you want to see what E looks like on your calculator, you can go on Desmos and look at the graph of E, but you can also get a calculator, and if I push Shift LN, then I get an E, and if I raise it just to the first power, that'll show me the value, the numeric value. So it's about 2.718281828. It looks like it goes on like that forever, but it's irrational number, kind of like pi, so it doesn't really repeat like that. So what you're going to be doing with this is a really good number for calculating interest. So that's what we use it for. So in the problem that we didn't do, the one that you're going to watch on number files, they use the formula for compound interest, which you may have seen before. The P is for principal, and R is the rate, N is the amount of times that you compound it. Like you can compound it semi-annually, or 4 times a year, or monthly, or daily. We're going to be doing a lot of daily calculations. That's compound interest. This is continuous interest. So this is compounding it every single second, like every nanosecond. This will actually give you, in the long run, more money. So what they have you do, we skip to the long problem where you would have figured this out on your own. And we're going to go ahead and do problem 10-178. I'm just going to walk through it. So it says in the last problem, which you watched the number files video for that, your calculations got closer and closer to the value of the number E. This research reveals that one use for the number E is the calculation of continuously compounded interest. The formula for continuous compounding is A equals P times E to the RT. So that's just one of your formulas that you need to save, or you can look it up on Google every time you need it. Where A is the total amount at any time, P is the principal, the initial amount, R is the interest rate, and T is the time period. So it says use the formula to calculate the amount Tabitha will have after investing her $10,000 for 1 year at 3% annual interest compounded continuously. How does this compare to the daily compounding? So all you're doing is plugging numbers into these two formulas. So this is the one that you would use for daily compounding. You would put 365 in for N, because that's how many days are in a year. Monthly compounding, you would put in 12, because there's 12 months in a year. Okay, this is your formula for continuous interest. So I'm not going to do all the problems because they do take a long time. But to compound daily, for this particular problem, she started out with $10,000. So I'm just plugging it in. It's 1 plus the interest rate was 3%. doing compounding it daily, so 365. And now the one is the N, that's for, sorry, the one is the T, that's for 1 year. And then, so you put this, just use the order of operations, and put that in your calculator. And you should get something kind of close to that. Sometimes we get a number that's a little bit different than our answer key because perhaps they rounded, or maybe you rounded and they didn't round, or something like that happens sometimes. And so don't get too upset if your numbers are like, a couple, maybe a cent off or something. I think um, mine were a little bit off. I wasn't rounding. I showed it like I rounded, but I actually left the number in my calculator. So I think your book might be rounding. They don't show all their steps, so I'm not sure what they rounded to. Anyway, here's how you do it for continuous compound. You just plug in your 10,000, and then E, and then R is 0.03, T is 1. And you'll notice I got different numbers using the different formulas. They're pretty much the same, but the difference is 3 cents. So you got 3 cents more. So big deal, right? You always get a little bit more. Sometimes if with big numbers you get a lot more if you do continuous interest, continuous compounding. So the book wants you to go through and suppose Tabitha invests her money for a longer period of time. How do the results for compounding daily and compounding continuously compare if she invests her money for 10 years, 20 years, 50 years? So how does that compare? Like, how does compound interest, if you compound it every day, compared to continuous? And I already kind of just told you that continuous, you're always going to get more. So I just did one of the problems. This was for the 10 years. So see, the only difference here is I put in a 10 for the for T, for time. Okay, and then I ended up, getting more money because I invested it for longer. And here I got more money also, and I got only 17 cents difference. But if I were to do the rest of these, I'll just read them off for you right here. You'd get a lot. Well, for 20 years, you only get 45 cents more. If you do continuous 50 years, you only get $2.76 more. But this is saying, letter C says, suppose a large investment group invests $10 billion, $10 billion at 8% annual interest. Compare the amount they will have after 1 year if the interest is compounded continuously with the amount they will have if the interest is compounded daily. Then compare the result after 10 years. So just to show you what a great big difference, I mean, the money, it adds up so much because these are exponential. Here's my formulas. Here's my 10 billion. And this is just doing the same thing we were doing before, but they had 8%. That was their interest rate for these investors. And then here, just doing the same thing, plugging the numbers in. But you'll see in my difference is $94,000-ish. That's a lot of money. Maybe not to the investors, it's not. But now they wanted me to do it, that was just for 1 year. They wanted me to show after 10 years. I don't know if you can see those numbers. So after 10 years, it would be $1,950,797. So then it says, what type of investors might benefit from continuous compounding rather than daily compounding? And it said investors have large amounts of money at higher interest rates, ideally for longer periods of time. So just know that there's a difference. If you can get continuous compound interest, that's going to get you a little more. Sometimes it's just a tiny little amount, depends on how big the numbers are that you're dealing with. And then 10-179, I don't really want to do the whole problem because I'm running out of time here, but I want you to see what the graphs look like. So I actually won't even do the problem. I just want to look at the graphs. So e to the x is it's kind of just like this. It's like an exponential, right? But it's not 3, it's 2.71 ish. So it doesn't, so you shouldn't be very surprised that it looks exactly like an exponential, you know, like y equals a times b to the x or whatever. It's just an exponential. And then its inverse is actually ln, natural log of x. And you might know that because we've learned how to solve for x by taking the inverse. Like when we have something raised up to the x power, we like to ln both sides or whatever. So this graph, it's a logarithm graph. I don't know if you really know a lot about logarithms yet, but you might know that graphs that are inverses of each other, they kind of have this reflection over the line y equals x. I think you probably know that. So I just wanted you to see what the graphs look like, and this is the last section in the chapter, so we'll probably get back around to some of this stuff later, but the main thing is that you know what E is, and we usually use it for compound interest.